right. Let's check. It says we're live, but I have no idea how to check this. There we go. We good? Yeah, I can't fix that. I have no idea how to fix that. It's yeah, I think I can fix it like this, but then I don't see presenter mode, so I'm just screwed, but it's okay. I don't actually need it. Cool. Okay, so I guess I had to remind people that we had class today since we had a failed class last week. So the topic I was going to talk about today is, since we've been learning about applied vulnerability research and analyzing real world systems, I was going to talk about the year that I spent attempting to find vulnerabilities and doing this. Hopefully, maybe convince some people or not convince some people to either do it or not do it. Of actually doing this on real world stuff. So I started this, and this was actually very helpful. I think I've hinted at a lot of these things during this class, but the goal was to try to bring it all together. So in February of 2022, I started doing pwn to own for Tesla, and the target was the Tesla. I formed a team with somebody anonymous, somebody who I knew. That'd be super weird if you just joined up. This actually is a good, point. Don't join up with random people that you only know through Twitter or something. If you've seen, there's the Google Project Zero blog posts where they dissect malware that people send. People say, hey, can you help me with hacking this thing to prominent security people? Not me, but other people. And it's a malicious, I think it was a VS Code project or something that would take over your computer. So don't team up with anonymous people, but I'm not going to tell you who it is. You may be able to guess based on, I don't know. And we focused on the Tesla firmware. We basically got a firmware dump from Tesla. Here's all the firmware, the stuff that runs on the machine, but then given no additional feedback. So we had to figure out what stuff was running on there. We tried to look at some of the classic examples through the web browser, things like that. But that was kind of, I don't know, you have to do a lot of recon, and then I wasn't super big on web, so I didn't want to go on web browser exploitation. So I really didn't want to go that route. So I started poking around to figure out what services were running on it, because you could see, and they actually had a pretty good architecture when we looked at it. It was they had each service defined. Each service ran in a jail that was limited to what it could do. There was, this is the weird bash stuff. So the feature that we ended up looking at was called this Tesla Light Show, where basically you could plug in a USB drive into your Tesla, and then it would detect, I think, an audio file and some other file format, and you could hit play. It would play the sound and move, synchronize time, the lights turning on and off, and the doors opening and closing, this kind of stuff. What was crazy is the file that parsed that file format to send out messages on the CAN bus was a bash script that just read in some binary format. And I tried to look at that for bugs, but I couldn't find anything. But the interesting thing was that this light show player called GST Play 1.0, passing in the song to play, this environment variable here. And it turned out that GST Play is a thing called GStreamer, which is an open source media library player that you can use, anyone can use. And the only thing that the script checked is that the file extension had ended in either, I think, .wav or .mp3. But if you notice, it doesn't actually pass any of that information here to GST Play 1.0. The only thing it does, it sets the audio sync to play it over ALSA, which is the Linux whatever audio system. Because this was running Linux under the hood. But there's nothing that says play a WAV file or play an MP3 file. So GST Play actually auto detects based on the file format and what the file is. And it turns out there's ton of what they call plugins of all different media parsing libraries. So this I was super excited about, because I said, oh, this is awesome. We can we have a choice. We can create a USB stick, right? Put up maybe a malicious file that we create on there, plug it in, and boom, it will I don't know if it'll auto play, but you hit one button and it plays. And that component had access to the CAN bus, so may be able to send CAN bus messages. The CAN bus is basically the internal network in the car where all the devices talk to each other. So like the steering wheel talks to the whatever motor that adjusts the wheels, this kind of stuff. So started to dig into GStreamer. And of course, my first thought was applying fuzzing because fuzzing is awesome and I wanted to get better at fuzzing. But it was actually incredibly painful to fuzz. Part of the reason was you build up, the way GStreamer works is you build up like a sequence of plugins because you can do like extract the audio from some file format and then do transformations to it and then do other things and create these like pipelines. But essentially each component acts as its own thread and then reads messages and then passes messages along to the next components. So building a fuzzing harness from this was incredibly, I guess I failed to do this, to actually like fuzz it because of a lot of the async message passing. The other incredibly difficult thing was that, so we tried fuzzing it just from the command line, which was another thing I tried, just like, hey, GST play, just start fuzzing. What ends up happening is it actually tries to play these files. And so you create a file, a song of whatever, some file format that plays for like a minute or two. And it just like, you hit timeouts and your fuzzing like throughput just goes through the roof. So, or through the floor. And it had massive problems, even though it's actually an OSS fuzz. So if you go look, you can see it on OSS fuzz and you think, well, this is a well-tested, well-fuzzed library. But in reality, only very little parts of this are actually harnessed to be fuzzed, which was another good thing I learned. So if you can't fuzz it, then what do you do? It's going to be interactive, by the way, now that we have multiple people. So you can't fuzz something, what do you do? What was that? Yeah, look at the code, or static analysis, right? Dynamic analysis doesn't work. Switch to static analysis. And even better than reading code would be using tools, right? So, well, actually, the very first thing I did was start grepping for strings like stir copy or anything that I knew would be at like gets, anything like this that you know like is bad. But that didn't actually, I don't even know if there are any hits. There definitely wasn't any useful results. Next, I thought, hey, let's use some like research. We've been doing research on this. We have a research tool called Arbiter that's able to use first static analysis to try to identify any places to malloc where an integer might overflow. And then it also does symbolic execution, I think, back maybe one or two steps, or maybe it's all symbolic execution. But you need to give this tool sources and sinks, and none of the built-in sources worked because they actually use this GStreamer uses glib, which is a different allocation system. But anyways, by adding those all in there, we actually did find one unchecked malloc. We'll see, look at it here, and you'll tell me if this is vulnerable, and there's a reason why. So this code here. So we have GSTQ array do expand. We get so you can just like in your own mind drop off the G. So uint is unsigned int. We get the element size, get the old size, the new size, and then we malloc. I think this is malloc 0, so malloc can 0 things out. The element size times the new size. So what's the bug here? What? Overflow. What kind of overflow? Like the multiplication. Will cause a what? So the model takes uint, right? That's a great question. I don't know. We'd have to look at it. Yeah, I think it actually takes a size t. Like a 64-bit number. So what would be the problem? Let's say hypothesize there is an integer overflow. Why is that a problem? Yes, that may or may not be a problem. Well, ideally, what this means is we will be uh, copying in element size times new size worth of data. I'm not sure. Yeah, so we can actually look here. First, we mem copy. This gets array 2. First, we mem copy into array 2 there at T2 times element size, and then mem copy T1 times element size. So if we can think that we're expanding, so this is like a classic just array or whatever expansion, right? So we've gone over the size. So we use some crazy formula here. I don't know crazy, but we use some formula to decide the new size. So we allocate the thing that's the new size, and then we copy the old size over. So if the thing that we allocated is smaller than our old size, we will then on that memory copy out of bounds and do a heap overwrite. So there's kind of two things always to keep in mind when you're looking at these things. A, integer overflow is, sorry, I should have made this bigger. Yeah, this new size is 50% bigger if we just want to go with that. But the point here is that an integer overflow by itself doesn't necessarily have any security implications, right? It's only when, in this case, it's being passed to malloc. So malloc would, the programmer, when they're multiplying two numbers together, is not going to get a, should not be getting a smaller number because they're allocating this. And if they need the bigger number, they're going to overwrite things. Now, let's look up gmalloc0. Hey, I was just talking about you. This is a bug that Arbiter found. Yeah. So yes, so G size is the same as size T. It's a 64-bit. So you're looking at this. Is there an integer overflow? If your life depended on it, could you say right now that it's an integer overflow? And tell me why. Not based on the fact that we're looking at it and I said it's a bug and a vulnerability. Yeah, why? Yeah, but it's an unsigned int. The argument to malloc0 is a size T. It is 32. It's unsigned int. Unsigned ints are 32 bits. But why isn't it promoted to a 64-bit? Because it's get passed to a 64-bit argument. So here, this exact thing right here. So element size, you can see up here is an unsigned int. New size is an unsigned int. You multiply them together, pass them to gmalloc0. But why is it not get? So what happens? What are the steps? Mm-hmm. Yeah. So is that an integer overflow or no? That's what you just said. You said an unsigned 32 times an unsigned 32 is an unsigned 32. And then that is extended. I think it would be signed. I guess it's unsigned. So yeah, it would be extended to a 64-bit. So just be a 32-bit value. Well, within the range of 32-bit values, it could be a 64-bit value. Yes, I don't know if anybody's on Twitch, but I have 6 experts, 6 experts in this room, and we could not come to a consensus. Are we at a consensus, or did I convince you in one way or the other? What do you mean by it? Because it's not underflow. Underflow? Yeah. It could underflow as a 32-bit value before it's casted. Because if it's being called the malloc and we need element size times new size, presumably that means we're going to be copying element size and new size, or at least element size, because this is a resizing operation. So we need more room. We allocate bigger space. We copy the old space to the new space. Yeah. Can't underflow. It can't underflow? Okay.
So, I mean, what you could have, right, is you could have element size and new size. It could be so large on one side that it wraps around to like, that's an over. It would still be so small to that. Right. But it's overflowing. It's not getting subtracted from where it.
All right, that's fair. Whatever, it doesn't matter. The point is, because this is vulnerable, which was my original question.
Yeah, like if you did like two massive values and overflow to say 0, exactly. Yeah. With that 0 32-bit, we just could extend to a 64-bit 0. Or same thing if it's a 1 or 2. And then, yeah. Yeah. Then we'll allocate a 2-byte buffer from fucking 1 billion byte.
Yeah. So the key thing that I found very annoying is when you look at something like this, you'd think, well, it's being passed to a 64-bit thing, so it should just, like, the multiplication operation should just operate on the 64 bits. Like, why truncate and then pass it to something immediately that's 64 bits? So this is why, actually, for a lot of things, having source code is super annoying, especially when you're dealing with these, like, truncations and possible overflows, these kind of things. This actually is why, like, Arbiter found this, and I looked at it and I was like, but why? Like, why is this vulnerable, right? And you can see it kind of in the assembly, but from the C specification, I can totally see a C where this is not vulnerable, because it, like, sure, if you multiplied them and set them to a new value, yes, that'd be very clear.
Yeah, like if you pass that to an auto bar, like that's gonna be 32 bits, and if you just pass that from one function, then
yeah, but like, why doesn't auto promote it to 64 bits, the resulting thing? Yeah, it could. The compiler could. It could be smart enough.
Even if it was 64 bits, I guess the question is whether or not those either parameter can be plugged up to just overflow 64 bit.
Correct.
Yeah,
which can you do on the two 32-bit numbers, unsigned numbers? Huh? This -1. No. Yep. Cool. That was a fun test. Okay. More tests. Cool. Yes. So, but it turns out that this is some queuing system, like I mentioned, that in the GStreamer library, you set up a pipeline of different plugins that talk to each other. So this is the queue size in between plugins, which you can't control from our perspective. So this was it is a vulnerability because this is a library that somebody could theoretically have code that let you do these things, but it was not that. The other then approach was after I think it was after I found this one, was say, hey, that's cool. There was a very clear, well, not a clear, but there was at least a instance of an integer overflow that could lead to a heap overflow. Like, so then my next tactic was grep for every single gmalloc in the entire code base, and manually audit every instance and just look kind of quickly and see if you see any patterns like this. And it turns out there's a ton. Why do you pop up? Oh, you're popping up here because it's already open. Goodbye. Let's see. Where'd you go? There we go. So here's one that I saw. So this is gmalloc size plus encoding comp setting length. I think size here, yeah, we can see here is a G unsigned int. I think this is also an unsigned int, so same thing, unsigned int plus unsigned int can cause an overflow, gets passed at a gmalloc, and it's the same type of thing, right? Here's the new data, and now we're mem copying in there, and you can see it's super interesting, right? Because if they had put this value into a variable, right? And said, okay, this is now the new size, like here. And if they just copied new size, that would be fine. But because you're trying to make a buffer that is made up of two different buffers, you have to have two different mem copies that use the separate instances of those size. So you're copying into their encoding plus comp setting lengths and then copying in their size. So by copying in there separately, that's when the integer overflow screws you and you can get a heap overflow because you can allocate a much smaller buffer for your large size buffer. And this was literally just like, yeah, grepping gmalloc, looking at every instance and auditing and looking at the code. Oh yeah. The problem is once you start digging into this, the first thing you need to do is to verify whether this is actually a vulnerability, because it turns out in order to trigger this, you need size or encoding comp setting length to be large. And it turns out there's a check here that your size is greater than max block size, which is I think 15 megs is this check. So there's like no possible way you can create a chunk that's that big and actually trigger this vulnerability. So this is a couple things we'll get into more, but like basically verifying static analysis results is very difficult. It'd be very exciting to see something, and if you spend too much time to start trying to pocket to trigger it necessarily without walking the call chain yourself and verifying things, you can easily miss these things. So looking at more things, here's an example where we have this swap line function, which is literally just, these are like, I think these are like maps. So there's like a map.data, there's an X and a Y, and they're trying to swap lines. I don't know why. This is some video codec. I think this is an AVI. But the idea is, yeah, stride times Y, and the Y data stride, I think these are all unsigned ints. And so this can overflow and you can get a problem here. But like, so tell me like this, can you tell if there's an overflow here, right? It's so difficult to tell. Like, sure, you don't have the types, but if you had the types, understanding all these rules and everything is such a pain in the butt. And this is actually, I think, what makes auditing in C hard for low-level vulnerabilities like this, because remembering the C specification and how that's going to map to the binary code is really annoying. So the trick that I learned, or that the trick that I used, was creating a very simple C file with the correct types and all the relevant operations. So essentially slicing out everything from that code, and then use Anger and see if it's feasible and say, is it possible starting from this function, as we'll see here. So I create a function for this test. So I use the same things, gint, gint32, whatever, y, width, height, bit count, size. I use the pound defines in the library, so I knew they would be like the exact types and everything. And then this, so this, yeah, the stride operations. Yeah, great. So this is where, so then all the go to successes, these were all the conditions that I took from all of those potential overflows and said, okay, if this is greater than or equal to size, then we have an overwrite go to success. If this is greater than, if this times y is less than 0, go to there. So bounds checking, essentially adding all of these in explicitly, telling Anger, do whatever. It's like empty function call from here, basically making y, width, height, bit count, and size in a fully self-contained program, having these all symbolic, and say, symbolically explore this, get me to success, and then boom, you can tell if it's actually like satisfied, if you can do that. And it's also helpful because you can then use those functions to then specify things. Like once you have a concrete value, like, okay, my height actually needs to be this, or my bit count needs to be this, it can tell you what other values you need to do for there. The other really fun part is I think I ran this on my ARM Mac because it didn't really matter. Like this was a Linux thing, but as long as the types are the right length and everything, it kind of doesn't matter, and Anger can deal with that. So yeah, I thought that was fun. So that was possible. So Anger said, yes, this is a real bug. And by looking at it, I said, great, by controlling those values, we can trigger an overwrite. But the target said no. This was, of course, after I invested time in creating a proof of concept AVI file that I could launch that triggered this overwrite. And then I launch it on the target and it doesn't work there. Anybody want to guess why? Nope, same code. I made sure it's the exact same version that was running on the Tesla that I was using. It's a good first check. Dead code? No, because I could trigger it on my version. Well,
there's more context to this function, and so
nope. I used the exact. I compiled the same binary, at least the intro GST play thing. They did not have that GStreamer module at all. Yes, so out of all of the possible modules and libraries that and plugin, they call them plugins that implement all these parsing libraries, I had of course just download. I think they have good, bad, and ugly as their three like ways of describing the quality of their modules, and I had the exact version correct of what those were, compiled them all, and was looking at them all, not realizing that actually not all of those are present on the Tesla. They had stopped some of them, so. That was incredibly annoying and a good lesson in understanding your attack surface and what's available and not getting too carried away by having some other thing. This definitely cost me, I don't know, a couple weeks probably. Then more malloc. I think I just had like I don't know if it was a file or something, but yes, I just had my grep results and I would go through them and make a list of potential ones and look at them. So now here we have one. GST buffer new allocate, wavepack 4 header size plus block size, and then mem copy block size onto, I guess it's out data, which comes from this buff. It's kind of complicated the way it works, but. So now here we have something that even if block size is now if it's 32 bits, we know, okay, if I can make that very large block size plus this small header size, again, another integer overflow, small thing, copying a very large thing. But the block size is limited, as we saw. We can't actually do 2 gigabytes. But I had figured out by trying to trigger another bug that you can use zlib in the MKV file format to compress a block, and the size check was done pre-compression, not post-compression. So you can have a 15 megabyte zlib compressed block size that would actually decompress to 4 gigs, which actually I only figured this out by trying to POC something else. So I knew there was this functionality in the target that I could leverage, but this was actually a massive pain because you had it had to be like wavepack 4 header size, which is probably like, I don't know, 20, 30, 40 hex, something like that, not a very large number. So this plus block size needed to be a 32-bit overflow. So it needed to be large but precise. And this was the decompressed version. And then as you so think about, you have a payload. It's very easy to get 0 bytes to compress to exactly, to decompress to exactly what you want. So you start with what you want, you compress it, but getting that, wait, what was the actual thing? Fuck. Anyways, wow, I had lost the thread there, but I had to write a tool that would try to get my payload and then add random bytes so that because it was doing this as it anyways, there was another bug to work around, so that doesn't really matter, but there was I wrote tooling to get the thing exactly where it needed to be. That was the thing. But then I did not exploit it. It was a 32-bit heap overwrite, so and that payload had to be almost 4 gigs to do that overwrite. And this required a ton of heap massaging to even survive the overwrite. And it was made even more difficult because there were multiple heap allocators. So first glib was using gmalloc, which was a slot allocator, but it would get data from malloc. And malloc was reallocating and moving things. It was a nightmare figuring that out. Plus there was multiple threads, like I said, going on. So there were multiple heaps in the memory space. And then even I actually did all that. You could do the heap overwrite, But then the question is then, of course, which I should have thought of beforehand, was assume you can do this. What do you overwrite in memory? Because this is a one-shot media file that gets read. You can't leak anything and then use it because it's not going to be useful to the next execution. And so there were some function pointers of things that you could allocate, but even manually looking and trying to symbolically explore on those things was difficult to find anything that was useful. And then I realized I was spending like months on this stupid thing when I should have just looked for other vulnerabilities and not wasted all my time on this. I also think it may have been, they may not even have paid for it because it was a bug in a third-party library, but I didn't quite think about that according to the pwn.own rules. So that was something to look for. So the outcome there was did not hack a Tesla, but I reported and fixed 5 vulnerabilities in GStreamer. So let's see if this opens up when I click that. What? Stop. So this was kind of cool, at least some stuff here. The other thing that was fun was Google actually has a bounty for security patches. So this is actually a tip if you're looking for something to do. This patch rewards program, they will pay you for improving. Let's see, improving fuzzing. They, at least at the time, would pay you for, like small improvements that have merit from a security standpoint. So like a buffer overflow like this that you find in open source stuff, like fixing that actually is worth a bounty. And anything that's in scope here is everything, I believe everything within OSS fuzz. So it was very funny. I submitted, I think it's even in here. I submitted the first of these, which was the good one that I talked about, this, the add WVPK header. And the person was like, hey, why don't you just write, like, you had a whole write-up about root cause. Like, why don't you just like write the patch too? And I was like, huh. And then I saw that thing and I was like, wait a minute, I should be writing these patches. So for some of these other ones, I wrote patches for them. And let's see. Oh, I have the arbiter one in here, which is, this GSTQ array. Cool. All right. From there, I turned the focus over to Mac OS, which is what I wanted to do and wanted to focus on. I started very broad. I had no idea what I wanted to initially look at. I started reading all of the Star OS internal books, starting from, I think book 1 is like user space. So you start reading there, and as I'd hit interesting things, I'd be like, oh, maybe I should go look at that. And I did some like iOS pwning with this OWASP mobile security testing guide, which is pretty good. Some interesting things that came out of that. Maybe interesting, I still can't tell. The installer, so when you double click a package and you get through those like installer steps on Mac OS, they execute arbitrary JavaScript. Like a package, a PKG file can have arbitrary JavaScript specified by the application that runs. So that's very weird. So I started to look at, especially with, you can expose different things to JavaScript that JavaScript can call. I didn't fully explore that, but I at least considered it. But it also turns out that JavaScript extensions can actually talk to kernel extensions. It's like incredibly weird. I think it's used to like, I don't know, verify if you're installing something, whether you have some driver or some kernel module or something. But this seems like super sketchy. And before I like explored it fully, I was like, would this even be a vulnerability? Because you can talk to it. Do you need to find a vulnerability in a kernel driver? But it's pretty interesting, at least to think about. And maybe it could be like a sandbox bypass where you send somebody a malicious APK, they double click on it, and then that thing talks to some kernel modules and is able to do bad stuff. So this stuff's weird. Then a month later, after like doing that initial exploration, I also, fun fact, has anybody ever like used IDA on something like huge, like 200 megs or something? Like doing the analysis? Yeah. Yeah, like the PHP interpreter, does it take like hours or to? Okay. Yeah, maybe it's the newer versions, but for this version, there was back in 2022, it was so slow, like doing the entire kernel cache and doing not the decompilation, but just the analysis, right? It took like hours and hours. I think it was like 13 gigs was my IDA file at the end. It's just absolutely massive. And then I found somewhere on the jailbreaking forums that they said that you can speed it up by closing the function view and some other UI elements that get updated every time it does some analysis, and that speeds it up so it's done in like an hour. It's like nuts, but I think they've actually like incorporated those things because it's absurd. So that was fun. Sock Fuzzer, I mentioned it a bunch, but I started looking at it in July. It was created by Ned, who you might remember, who gave a talk in here. And it was used to find Sock Puppet, which was a local privilege escalation kernel vulnerability. So from user space, there was a use after free and some socket stuff. And at the time, I think he was able to pocket for either full access or very full access. So cool vulnerability, and it was open source. And I mentioned this a little bit, but I'll go into why it was so cool. The basic idea is fuzz the networking part of XNU. So take which you can do with, I don't know, something like syscaller, which uses a virtual machine and runs the target. But one of the there's like 3 really cool ideas here. One is the user space Linux. So get this part of the kernel to run in Linux in user space so that you can apply things like ASAN to it and fuzz it using libfuzzer, which operates at like thousands of executions per second. I think like 2,000 or 3,000 executions per second per core, as opposed to using like a snapshot-based VM approach, which can do like hundreds of executions per second. So you're talking about 10, 30x speed up by using this new technique. Plus, you don't have to use KSAN. You can use the actual ASAN instrumentation, which is great. Super cool. And the other cool thing is this made debugging easy. When you had a crash or something that could crash, you can just use GDB. All the tools you're normally used to, you can use to debug the crash. Code coverage you can generate with gcov. It's like, it was super awesome. But to do this, you need to first like mock out the entire rest of the kernel, right? Everything that this module that you want to target, the networking module, every time it talks to something else, you need to return a value, which may or may not be useful to the program, or may, and if you mess that up, you could like not make progress. And I can talk about that a little bit. The fuzzer like wasn't finding anything, and I found the reason was one of the functions was mocked, or 2 of the functions were mocked incorrectly and was returning a value that was causing it to never close file descriptors, and it was like never fuzzing anything. The other super cool thing was creating a protobuf based mutator, which I think syscaller has something similar-ish. You can define like the parameters. One really cool thing that the protobuf mutator allows you to do is you can define something like, because you're writing the harness, so you write the harness translates protobuf input to either system calls, network IO, like packets incoming, packets outgoing, these kind of things. But one of the cool things is you can say like, okay, here's like an ioctl to something. You can say like, okay, I know this target has this specific ioctl commands, so you can write a protobuf mutator like that. But you can also say, or you can do a raw ioctl and just the fuzzer gives you bytes and you just send those bytes to the other side. So that allows the fuzzer the ability to try to explore and exercise more functionality than you necessarily had implemented in your harness and your protobuf mutator. This is actually, what was crazy is after like 4 months of fuzzing, it was able to synthesize IPv6 addresses using stuff like that, which was nuts. I still don't quite understand that, or just got luck. I guess you just get lucky once and then it reuses it across things and then things happen. I don't know, but it seems pretty wild. And it wasn't like zeros, like 128 zeros. That seems not very useful. So very first thing you do is just run it out of download it, compile it, run it. I ran it out of the box. Boom. found vulnerabilities. I was like, yes, this is going to be super easy summer. I'm already done. Turns out that vulnerability was fixed, and every vulnerability I fixed had already been fixed within that year. The reason was the public version of SockFuzzer was targeting an older version of XNU than I had in there. And because it wasn't like referencing the old thing, you had to like incorporate the entire operating system as like a library essentially in your app, and then mock out and chains out and sometimes patch things in the code to get it to run. So I was like, well, crap, every vulnerability I find will already be found by like Ned/Google, because Google has a month or a year head start on fuzzing everything. Which is actually not true based on how the results of this turned out, which I hadn't thought about while making this slide, but that was what I thought at the time. So the first order of business was updating the version of XNU in SockFuzzer. You think this would be easy. XNU is open source. It's already in there. This should be trivial. It is not. Anybody done any software development before? No, you've never written software? Nobody in this room? Just graduate students in computer science? Yeah, people have done software development. Is it easy or hard? Is it easier or harder when it's somebody else's code and somebody else's stuff? Yeah, it's really hard when it's somebody else's code, and it's even harder when it's multiple other people's code. So first, because the code that was in there was just changed. It wasn't a patch set that was applied to the code. So you had to first synthesize all the patches that existed in the current version, rip those out, then get the new version, apply the patches. Some of the patches don't apply cleanly. You need to figure out which ones are which, because of course the code changes. And then you need to mock out new functions. The kernel changes. So now there's new calls to new parts of the operating system that you need to figure out what to do. This was actually a really annoying problem that I think there could be research in here. But basically the approach was, because how to mock it, you don't really know is like how the function is used. What should you return? Like if you're mocking out this function, and there may be like hundreds of these, right? So like, are they called? Are they used? Who knows? What should you return? This is one super cool thing. So the other really cool thing about the fuzzing infrastructure in SockFuzzer, which is a great idea, is that with the protobufs, every single like protobuf message would A, have multiple commands, but B, have I can't remember what he calls it. I think of it as like fuzzer bytes. And so for instance, you're mocking something out, it could just return 0 all the time because you just want that to succeed. But maybe you as an attacker could actually trigger an error, right? And so if you actually return a fuzzer byte, it lets the fuzzer decide what the return value of that function is and return it. And so there's a really nice interface to just say like return fuzzing bytes. And then it just like based on those bytes that get passed in that protobuf message, whatever was used, it would use that byte. And then, so it'd be reproducible always based on that seed, essentially those seeds. But allowed the fuzzer to control that. So I guess null and 0 is the same thing. So actually the strategy is actually very simple. First, mock it out with an assert false. Just like if this is ever called, blow up, and then just like fuzz it for a little bit. And you'll hit the normal things, fix them, and then you'll get it to a point where on your machine it's fuzzing nicely, and then you, as we'll talk about in a second, submit it to the cluster, let it fuzz, and then it will find new things that you didn't mock out. You mock those out, update it, and then like slowly get it to where you've mocked everything useful over time. Which brings me to cluster fuzz. I have another name for this, but I definitely shouldn't say it. You can use your own thoughts. So cluster fuzz is very complex. It is very difficult to run. It's incredibly annoying, but when you get it working, you can easily scale up fuzzing from like, I don't know, 10 nodes to 100 nodes to 200 nodes to 1,000 nodes. You're also on Google Cloud Engine. You can use their preemptible instances too, which is excellent. It's a tenth of the cost of running those. So you're just like running them for very cheaply. And it has a ton of features. You can have multiple fuzzers, so you can just add fuzzers through the web interface. It does reproducibility analysis, so it will tell you in the interface whether a bug is reproducible or not. It does corpus minimization like every so often, so it'll take all the seeds that you're generating, minimize them for specific targets. It also does cross-target fertilization of seeds, so it will take like 2 targets and apply the seeds from one to the other to see if they're helpful or useful. Excuse me. It also can do regression testing, so it can identify if you have several versions, which version of the thing your bug was introduced in, which is pretty cool. And also, I think it keeps those seeds, the crashing seeds, so if that ever gets reintroduced later, it gets done. Oh yeah, version identification. So I used about 100 to 200 cores, depending on how I thought things were going. It also does like, I think there's a lot of room for research here because they do a lot of cool stuff, but it's not clear if like how much of it works or what are the right parameters. Because they do things like they do code coverage analysis and then across your fuzzers. And so they schedule more time and more cores to things that don't have as much code coverage. So things that start getting saturated, they stop getting coverage or stop getting executed, which may or may not be good. It kind of, I don't know. It's all, I think there's super interesting like game theory things here of like how to do this, how to optimize this, what is the right way to do that. I think if you just like took this, maybe even the current sock fuzzer, because it's good and updated and it's really complex of a target, and figured out what the best way to optimize cluster fuzz to like do something like this. It also makes me realize that, does anybody know offhand how many cores OSS fuzz says that it uses?
They say like 10,000, right?
10,000. Yeah, but it's across thousands of projects. Yeah. That's what's, you don't kind of like, you think like at this scale, everything is great. And as I saw in the GStreamer example, like GStreamer was in OSS fuzz. There were so many trivial vulnerabilities there because it only harnessed very specific things. And it's getting a fraction of those 10,000 cores competing with all those other projects. So, yeah.
They do weird timing things. Like they don't run it for like days or weeks at a time. They like do like little bursts of runs. And like...
Yeah, but is that effective? I think that's a key question, right? Like, is that effective? What's the right way to do this? They also do cool things. The other thing that they do is they don't do full corpus saturation. So they will like sometimes give some fuzzing instances like randomly a quarter of the corpus, which helps if you have timeouts or you have frequent crashes. That's another massive thing that came up is you'll see your fuzzing utilization as you get a very common crash, right? Your fuzzers fuzz and then hit a crash and then it has to do all the analysis. So you're actually not spending a ton of time actually fuzzing and generating new test cases. You're spending time dealing with this crash that's the same as all the other ones. So that's, I'll talk about this in a second, but anyways, this was a pain. This took like several weeks to set up correctly. Maybe correctly, I don't know. Okay, so yeah, and then also what I did with this, because I knew I could set up different fuzzers, was extending sock fuzzer. I said, hey, I'm not only interested in sockets, I would like to find vulnerabilities anywhere in this thing. So I extended it to the system V messages, which is a POSIX standard. Everybody knows system V. It's basically just like queues. You like create a message queue, you can put messages on the queue and pop messages off the queue. There's absolutely no bugs that I found in this like at all. And I think the code coverage was like incredibly high, like in the 90s of code coverage hits on the fuzzing corpus. It just like, there's nothing useful that came out of this fuzzer. So the things I learned, which I talked about, software development skills, and when I guess I say development, but it's not like undergrad, like I can code a whatever linked list or something like that. It's like, can you take a random piece of junk software that has an insane build system you've never used and like change it to do things or add to it or modify it and fight it when it does things wrong, or like debugging build errors, right? It's not just debugging code, like debugging build errors is like so frustrating. Or even when you have a software target and you want to like apply, I think some of you know this, you want to apply like fuzzing or AFL or whatever, you want to apply ASAN. Even sometimes getting it to use your GCC ASAN, or I can't remember, with Clang Analyzer or whatever it is, like, is sometimes non-trivial. Like, they don't take environment variables, they wipe environment variables, they hard code GCC. Like, it's like insane how difficult it is to actually do this stuff. Adding functionality. The other big thing I did that I thought was super helpful was automating the build deploy system. So as every time, like, I made a fork obviously of the system, every time I built it, whatever, I do use like not WebSockets, whatever the notify thing, the webhook on GitHub, it would webhook my server. I had a stupid Python thing that just every time it got hit would pull down the latest version, build it, and then deploy it to cluster fuzz. So I was always fuzzing and updating the latest version of whatever I was doing. That was super, super helpful for tightening that loop. And I think what this made me realize is basically, like, if you want to get into fuzzing, you need to be really good at security expertise to decide what to fuzz, because otherwise you'll never fuzz interesting things and never know what to do with the results, really. But also development, like software development, like making the fuzzer do what you want it to do is really important. Mm-hmm. Yeah, I mean, yes. Yeah. Yeah, and I think that's why more people don't, I mean, one of my theories of why more people don't do it is because of this. It requires this kind of unique-ish set of skills that, like, I know some really good hackers, I don't know if they'd spend 3 days like combing through CMake errors and like understanding CMake of how to do a thing and add a new thing. Like, it's just like, I don't know, like some people just hate that stuff. And so you have to be willing to deal with all this BS garbage to like get to the thing. Cause as we'll see, once you like can harness fuzzing, it's fucking great. Cool. So I set this up and then bam, I did find my first bug right away. I already have where the vulnerability here is. So even with knowing that that line is vulnerable with the comment, why is it vulnerable? I remember linked lists. I just say you didn't need to know how to program linked lists, but do you remember how to program linked lists? So what's the code doing first? What's this code around where I said vulnerability? What is this for loop doing? Yeah, to do what? Yeah, so we had this NDVR entry, which we're on this multi-adder free, calls free and does everything, right? But I think it's NDriver, but I don't know. I think this is in some network. I mean, it's a networking module because this is the only thing that was hardest. But yeah, NDriver entry. So this is the thing we're freeing. So this gets freed, but it's in a linked list. So we're iterating over this linked list, trying to remove it from the list. So what's the bug? And this right here is why fuzzing is amazing. Because I have 6 experts in this room. You couldn't tell me within 20 seconds of looking at 5 lines of code, pointing out exactly where the vulnerability is, why there's a vulnerability there. But the fuzzer did. And the fuzzer found it, and it didn't care why. And this one was a completely reproducible bug. Look at the code. Yeah, the ellipses aren't important at all. I'm not hiding anything in the ellipses. The bug is here in the code. The NDriver entry is in this list. And it gets freed. Is it possible to have 2 of the same name list? No, good call. So let's walk through it. So first thing we do, current, NP, ND, multi-adders, get current. If current, I think we could remove this one. If current is equal, so if the current is the thing we're interested in, right? The head of the list is the thing we're interested in. Then set ND multi-headers, which is the head, the pointer to the head, to current next. So we've removed that from the list. We'll never iterate over that thing again. Cool. Okay. So that seems fine, right? If the thing is at the head of the list, is it not fine? Your fingers up. Okay. And so if it is, then we boom and we free it. Great. So we know the vulnerability is here. Okay, so the next case. So it's not the first one. So what do we do? So first entry, current is the front, is where we are. Current equals current.next. There you go. And then what does it check? What does the if condition check? So just step through it. You went through too quick. So the first one, we set current equal to the next one. And then what do we check in the if condition? If current next is the one we're interested in. So the only way you can trigger this bug is if the thing you're looking is in the second position in the list, which is like insane. Like the fact that this, I can't remember if the POC used 2 or 3 or if you needed 3 or if there's some weird thing, but oh yeah, because cur not equal to null. That's the other check, right? So you would do cur equals cur nec. Well, I guess that would mean if you can't just have one would be the same, 2 would be, anyways. So yeah, you needed, I think it was that you needed a list of 3, and the second one had to be the one that you were deleting, the same one that you were deleting in order to trigger this bug. And then you have a use after free. So you have a thing where this pointer is still on this linked list, but that has been freed, which is wild because it took me way longer than it took you guys to. And I had the bug report that said, here's the exact thing, here's the use, here's the free, and a debuggable thing that I had to step through to see why it was. Because you look at this code and it kind of looks fine. Like, I don't know, it looks like a normal like link list checking code that you just would write. And I didn't put the dates on here. I think this one was around for 20 years or something. 18 years maybe. Because that was a fun thing. Once you now know the root cause and you know exactly what to look for, you can go back previous versions and figure it out when it was introduced. So this kind of then became, I think, this is what I think of, and I think I talked about this a little bit. This was like the day in the life of the fuzzer, is like you, not me, the fuzzer, but I guess the fuzzer farmer. You like wake up, you check cluster fuzz. Did I find any cool bugs? Any new crashes? Awesome. The other thing I should mention is that I used like ASAN, but since you have them, I used I think UBSAN as well, which was useless, and I should not have done that because it's just like so much garbage bugs that like I don't care about the integer overflow in the timer in the whatever sequence number calculation inside the TCP library. Like it was like insane. But then you have to fix them because if you don't fix them, your fuzzing utilization goes down and you're wasting time. So the interesting thing was, like, did you find any new crashes? If so, try to triage them and do the root cause. A key aspect here is like, is it reproducible or not? If it's reproducible, great. Then you can try to do things like minimization. So you can use like, and I think Cluster Fuzz does that too. I should have mentioned that. But the other thing you actually want to do is fix the crash. Like if you can quickly determine what it is, and if it's not useful to you, fix it so that way you can keep fuzzing. Like this is actually kind of the FlackJack like future fuzz thing. It's like, because this actually is what you want to do. Like, okay, you found it once, but especially as you find it, you'll keep getting seeds that are closer and closer to it. And so that crash will happen over and over again. And it becomes like your fuzzing throughput just massively decreases. Then if you've done that, or around that same time, also download all the seeds, generate a coverage report, and then try to figure out why you're not hitting code. So you look through the code. I think I had a fancy-ish setup where I would run it and then pull down the coverage and then load the coverage into Emacs, so it would get like annotated on the side so I could see green and red what was or was not. You can also use the standard like gcov reports. So then this would be like your, okay, we're not hitting this thing. Do I need to add, like, do I need to increase the harness? Like, what's going wrong? Like, why aren't we doing this? And it's basically just this over and over and over again. And then I think the last step here is like, is like decide, do I want to harness something else? Like, do I think I've wrung out everything I can do from this specific target? So then a month later, I think this is kind of interesting. I don't remember exactly why, like, because that first bug like shook out pretty quickly, but this next one took. Oh yeah, I do know why actually. The second bug was an unreproducible heap underwrite. So something was allocated on the heap and it was underwriting it. The reason, this is the code. IFP, like this IF index for some reason, like, so this is the list of all of the interfaces that the kernel has. And it used a -1 indexing. So it started at 1 and then reference it in an array as -1. And it was as you can see here, a 16-bit integer. So if you could overflow that, get it to be 0 get it to be 0, then it would index negatively and go outside the array and write something outside of that array. And this was actually the big problem with the fuzzer. So it was unreproducible because the fuzzer needed to create 65,000 interfaces. And it's never gonna, like, the fuzzer is not gonna synthesize a seed that just does that over and over again, right? Like, the way fuzzers work and the way code coverage is created, it's just, at a certain point, it becomes uninteresting and it's not going to continue doing that. But why did it trigger then if the fuzzer could never do that? No. Why does syscaller have unreproducible bugs? State buildup. Yeah. So the harness tried as much as it could to reset the state, but it's very difficult to make sure you've cleared up everything. And this was something that was not cleared up. And so over the course of one fuzzing session, throughout all of the possible seeds, there were over 65,000 things created. And that just happened to happen for one of them, triggered this bug, and boom. So this was the nice thing about fuzzing is you have this crash that's like, this thing definitely happened, and here's the bug. Here's the bug. There was a memory corruption that happened, but the seed that it says that it happened with does not reproduce that bug. And it may not have a lot of information about how to trigger that bug anyways, that seed. So this is, I think, another area of research that I think is super fruitful is like, how do we take these unreproducible bugs and try to get the fuzzer to either reproduce them or automatically give the fuzzer a way to like change some of these variables maybe. So like if we notice that, I don't know, maybe it's a, you don't need to know you have a crash, but maybe if it's, hey, I know that I can like call this system call over and over again, and I can do it over and over again, and some value, this index gets incremented, right? Like, why not just let the pointer or let the fuzzer control the value of that value? Because then it could generate a thing that says, okay, set the index to this value and then do one more system call, and then boom, now you have an overwrite, which would tell you that, like, much more closely link the like what is actually going on in this root cause. Yeah, I can't remember. I think you can also do something interesting starting from the unreproducible crashes. I think that's what they do.
Yeah, they claim it's from like static analysis reports or fuzzing crash reports.
Interesting.
From there, they kind of direct the fuzzer towards satisfying some conditions that lead to the crash.
See, but that's
like
yeah. I still don't think a fuzzer would generate like 65,000 inputs. That's what I think. Like, I think for some of these things, right? For some of these bugs where it's like a crazy integer overflow that if you do this. So anyways, I think there's other approaches, but yeah. But a similar idea. Then I spent basically October trying to POC that bug. So you had to create 65,000 network interfaces. It took hours because of linked list behavior. There was like some double linked list iteration, and I graphed it. It's an exponential buildup every time you added an interface. There are also limits on the maximum number of interfaces you could have per type that were less than this. So you had to like properly create different types of network interfaces. I started like at one point because I could use virtual machines because I was running on the and take snapshots because I had access to x86 machines. So I would like snapshot the machine with like 65,000 things so that I could like trigger this and figure it out. Anyways, by really studying the code, I figured out you could delete the interface, but it would still, that number didn't get decremented because those, like, it was like the space for that interface was allocated and never freed. So you could add an interface, delete it, add a new interface, and then delete it. It had to be different names, and it would be way faster. So that would work. But creating a POC that could overwrite a useful pointer took like 3 weeks of insane time because I wanted to like get that, because that was a pointer that was written, and I wanted to have that overwrite happen somewhere where I could actually control bits. In the end, I realized, why am I doing this? This is not going to increase my payout of this bug. I need to just move on and POC another bug. I could have spent that 3 weeks extending the fuzzer because, well, as we'll see, retargeting the fuzzer like pops stuff out. So in November, I targeted the PF module, which is packet filtering. I basically studying and figuring out, the great thing is the BSD underpinnings. So there's a lot of good docs. So like the character device life cycle, because anytime you need to fuzz something, you need to make sure like the thing is initialized, it's done, which should have made state cleanup easier because you have loading the module and then interacting with it and then unloading the module. So it should clean up nicely. Do all that. And then boom, I think right after that, the third bug popped out. This was like, these were where I started to be like, wow, the fuzzer is like legit crazy. Like it created a dynamic address. There was some limit on the number of dynamic addresses you could use in a table, but then, and you could like cause it to free something. I think this was probably an unreproducible bug if it had these dynamic addresses, but I don't really have all the details of that. Anyways, I'm not going to go into the code of these because, oh, yeah, I am going to go here. Yeah, I don't remember where this bug is, so this isn't very useful. But I do have a whole write-up on this if you're interested. I'm happy to. Anyways, basically, like, it caused something to be freed, but there was still a reference to that somewhere else, and so that was used. The fourth bug was another use after free, which had an insanely complicated root cause that I don't want to get into because I read it and I don't understand it like at all to even try to explain it to you now. But the key thing here was that the PF module had two different ways to add rules, one in dev PFM and one in dev PF. I still to this day have absolutely no idea what the difference is. There's no documentation that tells you when to use one versus the other. And as I was writing the fuzzing harness, I said, you can specify the device number that it comes from, and there are two. Should I modify it? And I said, sure, why not? And it turns out that it literally, the only reason this worked is when you're calling delete rule by owner on one module or on one of those interfaces that you had set those from the other. And for some reason, it like did not clean that up and kept those references and skipped it, even though pointers to them got removed. And so you had this use after free, which was crazy. Anyways, that was a very good lesson. Couldn't have found the fourth bug without it. It also was a good instance of like, just like target something interesting and like bugs will fall out because you're probably, people haven't fuzzed it yet. And each of these was also very old. I think they were probably 10 plus years old. like, I guess I should also say these were all root to kernel bugs. Anyways, then after that, extended sock fuzzer again, targeted the TTY kernel module. So this handles all the, I thought it'd be a good one. It was another kernel character device because once you have like a framework for doing one, it's like super easy to try to apply that to other ones. Then the fifth bug popped out of there pretty quickly. Another use after free in the TTY module. This one I think may have been like actually exploitable, but we can talk about it in a second, maybe. Yeah, but this was super interesting. What I liked about this bug is like there was like 5 steps. Like the fuzzer had to generate a sequence of 5 operations in order to actually trigger this. So like first open this PTMX device, then open the TTYS device, then close the TTYS device. This is where like const TTY would be cleared. Then set the PTMX's device TTY as const TTY by issuing this semi-octal. Now close it, which frees PTMX TTY, but const TTY now points to this now freed TTY, and you can use const. There's like the console TTY. This bug is almost as old as me. It went back to BSD 4.3, I think, which in that case, it didn't, I mean, yeah, these things, you did need root, so it kind of didn't matter, or it didn't matter back then, but it's like, I don't know, to me, it's super interesting seeing like how old these bugs have just been there forever. But like, if you just looked at this code, like, was like, you know, think like, because this const TTY was a global pointer. So you could, I think it was like console TTY, like where the console's output would go. And I think with this, because these TTY structures had function pointers, and this was before they did the like binning of different data, I think this one could be one that you could actually like get pointer control and mess with function pointers and actually like do some damage. But I said, found it, pocked it, and moved on to the next bug because that is a good strategy. And so my final attempt was, I realized I did not optimize anything for economic purposes. I was like, I keep finding these root to kernel exploits, which don't pay as well as a user space to kernel. Why is that? And I said, well, it's because you keep targeting things like the PF module, which can only be talked to by root, or the console, which can only be talked to by root. This is why, this is why you're doing that. So I then looked for kernel modules accessible by non-root users, found that SMB is done in the kernel, but I failed at harnessing it fully. The key problem was it used which I think is something we've seen even in Linux, it uses like queue-based processing of messages. So like a request comes in and then a message gets put on a queue and there's another thread running that reads from that queue and does stuff. And so like, you want to be able to actually really fuzz that by like, instead of putting it on the queue, screw the queue, just call the thing and like have it do the thing and then come back. But like, I just couldn't get that working enough. I was like hitting errors and exceptions and it was not very useful. But I did find, I did find one good, or a heap overread, but it doesn't get paid for. So I didn't really report it yet, which I should. I tried it this morning. It doesn't work, but I don't think the vulnerable code looks like it's still there. It's just the interface changed, so my POC doesn't work currently. But I should just submit that. Anyways, my final thoughts on bug bounties. Bug bounty is very tough mentally. Like if you're doing this solely on your own. It's tough mentally for a couple reasons. One is like the economic factor. You don't know when you're going to hit the jackpot and get paid. So like relying on this as your sole source of income, unless you can live very, very, very cheaply, I don't know that I'd necessarily recommend that. As like a fun side project, I think it's great. I think you have to decide what you want to do and optimize for just find bug, POC bug, submit bug, like write up bug, submit bug. I think if you can do that loop pretty tightly, then that's not so bad. But like doing exploitation where you realize you spent a month trying to like exploit something instead of pocket, like that's like, not a good way to do. Because bug bounty is not the same as exploit development, right? Full exploits, you're much better off harnessing a new target rather than pocking, like fully exploiting or pocking a binary, unless you have something really cool. You can make a living doing this, I think, if you want to. The downsides for sure is you need to like hyper specialize. Like this is what I think the trap that a lot of people fall into, and this is even people that I've talked to that do exploit development for a living, is like you're paid because you know the target very well and you can find stuff. And like towards the end, going from the fuzzer's output, which is this proto buff of these system calls, going to that to a CPOC for me became very easy because I got used to that. I understood how to do this. But like at the beginning, it took me a week to create the POC from the fuzzer output. And the time you spend learning a new target is time that you're not getting paid for finding stuff. So I think that's definitely a downside. I don't know how to combat that. Maybe part of a team or something would be helpful because it gets easier. Your knowledge of a target gets easier over time. So you're more likely to find stuff. Yeah. So anyways, that was my, for those of you that weren't here at the beginning, my year in the vulnerability mines. Any questions? So it's looking at the Twitch stream. It was interesting. It paid less over time, and I don't know. Also, the first bugs were like 15K, and then the last bug was like 10K. Even though I'm pretty sure that one was like worse, but they had also introduced more of those mitigations. So I think maybe that was like their thing. Whereas I've heard a good word on the street is a good like user space to kernel bug would be 50K. And then according to their website, you can get like, if you can show that it, like especially user space stuff, if you can show that it's user space in the iOS sandbox, so in the app sandbox, if that exists, that's like a massive multiplier. I think if you can demonstrate persistence, or like if it's a like, they actually, I think will pay out, although I don't know anybody that's done that. I don't know if anybody's claimed that publicly, but like if you had a fully remote thing, it's like what, $1 million. That would be like chaining 5 of these vulnerabilities together, right? Because it's never going to be one shot. So yeah, and I think with the security features they've implemented, it's like harder. I wonder if you'd be better off looking at the new private cloud compute system. That's their, like the thing that they have that they announced like a $2 million bounty. I don't know. It's hard to say. So yeah, and that's part of it. I think you could get paid more by having something that actually achieved like kernel read, kernel write with a use after free. But I don't know that it was worth the effort to invest that unless you already knew how to do it.
They don't really specify publicly.
No, they do not. They specify ranges publicly. And I think like also the quality of your write-up definitely, I mean, I don't know if that influences payout, but it definitely will get your bugs fixed faster by having a good write-up with the root cause and a POC and that kind of stuff. Other questions? Yeah.
Anybody that actually got paid without POCs, just like a pressure balloon?
Anybody that got paid without POCs? I don't think so. I mean,
is that a requirement or?
Yeah, I don't know if it's a requirement. Like you have to write stuff. So my first bug was submitted through email because that was their only mechanism. But now they have actually a very cool website that is like shockingly polished for a website that's going to be used by like 20, I don't know, hundreds of people, maybe max. But it tracks like your submission as it goes through the thing. Once you get paid, there's like balloons that come down and stuff like on your phone with the congratulations thing. It's like wild. I was like, anyways, I was like shocked that somebody spent the time on it, but it's very cool. And they had the CVE numbers in there too and everything like that. So yeah, that would be interesting finding out. I think most people have POCs. Like, there's also a whole other route to go. I know there's people online, I'm forgetting their names, but on Twitter, there's a lot of people that do like privilege escalation in other ways. So like user space to root through like set UID bypasses or weirdness in the file system, like that kind of stuff. So like not necessarily kernel stuff, but outside of there. Yeah, I would think you need like, the way I always think about it is your write-up should be what you as the developer would want if you had to go fix this bug. So like you want input that like crash, like does the crash of the thing. Like what I would do is I'd write up like an overview statement of what I thought it was, like a root cause section of analysis of what I thought the root cause was, including code snippets and everything. And then like a POC submission file that you send. And then a KSAN report of a target where I had run it and got a KSAN report and said like, this was like the latest OS version on this, like here's a KSAN report, which also I think proves that it is possible. Because I think it's, I think maybe a tricky thing would probably be race conditions, right? Like, you could have a POC that's not super reliable, but yeah, I don't know what they would do with that. I think you have to be okay with like submitting something and not getting paid because you just can't control the process, right, of what happens afterwards. So it also is, you got to remember there's like people on the other side. Like it's not a machine. So like I realized that remembered it while looking through my reports today. Like my first one's like you submit and then like they're like, yay, you get a CV, you're getting paid, and like, yay, and then the thing's released and then it comes out. Like for some of the later ones, the system was like, okay, you submitted it, great. Like, hey, good news, it's fixed in this version. And I was like, okay, but like, am I getting paid? How much am I getting paid? Like, I would like to know these things. It's just like, I think like the timing of those things, because there's people, right? It's just like the thing where they decide that it may not be done before it ships. Like, who knows? Yeah, it was fun. I did really like proposing a fix and then looking at the source code and seeing how different the fix was. Because sometimes you could see them like go in and clean up the code because it probably hadn't been touched in years versus, yeah. So I thought that was interesting.
What was your setup like?
My setup? I had like my main laptop I was using. I had a separate backup x86, an old like Intel Touch Bar Mac, because the Intel Touch Bar Mac you could run virtual machine like VMware and run a Mac VM in there. So I would use that for testing. The problem is towards the end that was not able to run like the latest version of the operating system. So it's actually now a useless setup. And yeah, you could set up by setting boot args, you can tell it when you hit an exception to like listen on a network interface and an IP address maybe, and then you can connect LLDB to it to debug remotely the kernel through there. So then from there, that's where I'd get like the KSAN report would be somewhere in memory. I think there's a way to dump it, but I was never able to figure it out. So I would always like walk up the call stack and like dump the KSAN report and from LLDB. That was my main setup. But then I had like Linux machines running, like one was the build server. I had like a local dev Linux box that I would like test locally fuzzing stuff, and then like the cluster running. Yeah, just getting to that point is like super annoying of like getting all the stuff ready. Or like you find it, and that's what like building that up over time, that's why you become so much quicker at this stuff is like I didn't track it, but I'm sure if I tracked my time from bug to bug report from fuzzer to Apple submission, like bug bounty submission, it got like pretty short. I think by the end I was doing it like 3 days. Like find report, like pocket, write up, submit, boom, and then like move on to the next one. Whereas I think the first one took me a month and a half because I needed to I've got to debug this thing. I have to like figure this out. Cool. All right, thank you. We are done with class.